In this video, we're going to talk about factorization.
It's the transformation of a polynomial from its standard form into the factored form. P of x equals a0 plus a1x plus a2x squared, and so on, up to an x to the power n, which can also be written as an times x minus r1, x minus r2, and so on, up to x minus rn, with r1, r2, and so on up to rn belonging to the real or complex numbers, such that p of ri equals 0 for all I. We call these values the roots, or zeros, of p. Here's a simple example. 2x squared minus 10x plus 12 equals 2 times x minus 2, x minus 3. Now let's move to degree 1.
A first-degree polynomial has the form ax plus b.
Factoring out a gives a times x plus b over a, or a x minus negative b over a. So the root is minus b over a. For example, p of x equals 2x plus 4, which factors to 2 times x plus 2. Hence the root is minus 2. Another example, p of x equals 3x minus 2, which factors to 3 times x minus 2 over 3, so the root is 2 over 3.
Next, we consider second-degree polynomials. A second-degree polynomial has the form p of x equals ax squared plus bx plus c. We compute the discriminant, delta, equals to b squared minus 4ac. If delta is greater than 0, the polynomial has two distinct real roots, r1 and r2, which are equal to minus b plus or minus the square root of delta all over 2a. If delta equals 0, there is one real double root equal to minus b over 2a. If delta is less than 0, there are two complex roots that are equal to minus b plus or minus I times the square root of the absolute value of delta all over 2a. Let's look at some examples. P of x equals x squared plus 4x plus 3. Delta is 4 squared minus 4 times 1 times 3, which is 4, greater than 0. r1 and r2 are equal to minus 4 plus or minus the square root of 4 all over 2. So the roots are minus 1 and minus 3. The factorization is x plus 1 times x plus 3. Now, p of x equals 2x squared minus 4x plus 2. Delta is 0. So the root is 4 over 2 times 2, which gives 1. The factorization is 2, x minus 1 squared. Remember, if delta equals 0, the equation has one real double solution. Now, let's see an example with a negative discriminant. P of x equals x squared plus 2x plus 5. Delta equals minus 16. The square root of the absolute value of delta is 4. r1 equals minus 2 plus 4i all over 2, which is minus 1 plus 2i. r2 is the conjugate of r1, which is minus 1 minus 2i. So x squared plus 2x plus 5 factors as x plus 1 minus 2i times x plus 1 plus 2i. Now, let's move to degree 3. To start, we use the Rational Root Theorem, which gives a list of all possible rational roots. This theorem can be applied to polynomials of any degree as long as the coefficients are rational. Here, Q denotes the set of rational numbers, written in the form a over b, where a and b are integers and b is not 0. Numbers like square root of 2, pi, or e are irrational. Now, let's see the rational root theorem in action with a cubic polynomial. P of x equals x cubed minus 6x squared plus 11x minus 6. The divisors of the constant term, minus 6, are minus 6, minus 3, minus 2, minus 1, 1, 2, 3, and 6. The divisors of the leading coefficient, 1, are minus 1 and 1. Then we divide each divisor of the constant term by each divisor of the leading coefficient to obtain all possible candidate roots. So the candidate roots are minus 6, minus 3, minus 2, minus 1, 1, 2, 3, and 6. P of 1, 2, and 3 are equal to 0, so 1, 2, and 3 are roots. The remaining candidates are not roots. Hence, P of x factors as x minus 1 times x minus 2 times x minus 3. Now, consider this one. P of x equals 1/3 x cubed minus 7/3 x plus 2. To apply the rational root theorem, we multiply by 3, x cubed minus 7x plus 6. A belongs to minus 6, minus 3, minus 2, minus 1, 1, 2, 3, and 6. And B belongs to minus 1 and 1. Then we divide A by B to get all candidate roots, and we substitute them into the polynomial to find the actual roots. So the roots are 1, 2, and minus 3. Therefore, P of x equals 1/3 times x plus 3, x minus 1, x minus 2. Let's try this polynomial. P of x equals x cubed minus x squared minus 2x plus 2. The candidate roots are minus 2, minus 1, 1, and 2. P of 1 equals 0, so 1 is a root. In the theorem, if a rational root exists, it must be in the list, so the other roots aren't rational. To find the remaining roots, there are several possible methods. For example, we can use the method of identification. Since R1 is equal to 1, and according to the definition of factorization, the polynomial can be written as x minus 1, x minus R2, x minus R3. Let Q of x equals ax squared plus bx plus c, therefore P of x equals x minus 1 times Q of x. After expanding and identifying the coefficients, we find that a equals 1, b equals 0, and c equals minus 2. Therefore, Q of x equals x squared minus 2. So the factorization of P of x is x minus 1, x squared minus 2. Next, we factor x squared minus 2 using the difference of squares formula. As a result, we obtain x minus the square root of 2 times x plus the square root of 2. So the polynomial becomes x minus 1 times x minus the square root of 2 times x plus the square root of 2. Or we can use Euclidean division to find the remaining roots. First, we divide the first term of the polynomial, x cubed, by the first term of the divisor, x, and we get x squared. Next, we multiply x squared by the divisor, and we obtain x cubed minus x squared. Then we subtract x cubed minus x squared from the polynomial, and we get minus 2x plus 2. After that, we repeat the same steps with 2. We divide the first term of the new polynomial, which is minus 2x plus 2, by the first term of the divisor, x. Then we multiply the result by the divisor, and after subtraction, we obtain a remainder equal to 0. Now, let's discuss some limitations of the rational root theorem. Limitation 1. The number of candidate roots can be very large. For example, for the polynomial 6x cubed minus 7x squared minus 40x plus 21, we obtain 24 candidate roots. Limitation 2. The rational root theorem cannot be applied if the coefficients of the polynomial are not rational numbers. For example, we cannot apply the theorem here because the square root of 2 is not rational. Limitation 3. A polynomial may have no rational roots, even if all coefficients are rational. In the example in front of you, we cannot use Euclidean division or identification because all the roots are irrational. This is different from the examples we saw before, which had at least one rational root. Here, we can use Newton's method, for example, to approximate the root. That's all for today. In the next video, I will explain solutions for all three limitations and show examples. See you then!